In this screencast, we'll talk about bounded and unbounded quantifiers, or bounded and unbounded quantification. So there are two types of quantifiers, or two types of quantification in theoretical computer science and mathematical logic. Existential, bounded existential quantification, unbounded existential quantification, and bounded universal quantification, and unbounded universal quantification. So there exists t less than or equal to y, for which this predicate pt, where t is one of the arguments, the first argument, and some other arguments, x1 through xn, this quantified statement is true if and only if this predicate of n plus 1 arguments is true for some value of t in the closed interval from 0 to y. And then there's a case of unbounded quantification, where we quantify t over the set of natural numbers. So we do not put any upper bound. So there exists t such that p of t x1 through xn. So this statement is true if and only if, this is the statement, or evaluates to 1. It's just to be consistent, when this is 1. If and only if the predicate t of x1 through xn is true for some value of t in a set of natural numbers from 0 up to infinity, so long as t is a natural number. So let's consider a couple of examples. Let's define this predicate p of tx to be 1 or true, and 0. So if it is 1, if t modulo 2 is equal to 0. So if t is an even number and t is strictly greater than x, and 0 otherwise. So it's a predicate of two arguments. So there exists t less than or equal to 10, for which p of t and 2. So there exists a number in the interval from 0 to 10, which is even and strictly greater than 2. And obviously this is 1. Why? Because, well, let's say 4, right? P of 4 and 2 is true because 4 is an even number. 4 modulo 2 is equal to 0. Right? There's no remainder when we divide 4 by 2, and 4 is greater than 2, and 4 is in that closed interval from 0 to 10. On the other hand, well, let's construct a predicate, existentially quantified, bounded existentially quantified predicate statement that is going to be false, right? So there exists a t less than or equal to 10 um, for which pt20, right, is true. That's going to be false. That's going to be false in this case. All right, so let's grab some space and continue with universal quantification, bounded and unbounded. So it is similar to existential quantification, bounded, in the sense that we are iterating in the bounded case over a closed set of values from 0 to y. So for all t less than or equal to y is an upper bound, p of t and some other arguments is true if and only if this predicate of n plus 1 arguments is true for every t is in that interval from 0 to y. So here's an example. Let's define this predicate p of t and x to mean that t is strictly less than x. Right, then let's construct a universally quantified statement, universally bounded quantified statement, which is true. So for all t less than or equal to 20, p of t and 21, right? That's going to be true because every t in that interval from 0 to 20 is going to be strictly less than 21. Okay, let's talk about unbounded universal quantification. So for all t, pt x1 through xn, so this is unbounded universally quantified statement. This is going to be equal to 1. All right, so let's, for consistency, square bracket this 2. So this is equal to 1 if this predicate pt x1 through xn is true for every value of t, so long as t is in the natural number. So let's construct a simple predicate just to illustrate unbounded universally unbounded quantifier, unbounded universal quantifier rather. So let's say p of t is even or t is odd. So then for all t, pt is going to be true because every number is either odd or even. Natural number is either odd or even.